This is a part 2 video of the project that we are trying to predict the output given a sequence of the events using a transformer architecture with the transfer learning and fine-tuning. If you haven't watched the first part, I will put the link in the description so you can watch that one first. On the previous part, we tried to develop a vanilla version of the transformer architecture with the BERT, but we didn't get quite very good results. In this part, we talk about how we can improve the result. We can use a distilled version of the BERT, which uses the teacher-student architecture to come up with a smaller size network to reduce the model capacity. We also look at different ways like LoRA and quantized version of it, the QLoRA, and finally, for example, other methods such as data augmentation with self-supervised method. So we have a lot to get into. Without further ado, let's jump right into it. Welcome everyone to your channel AI Fun Fact for All. For those of you who are new to this channel, my name is Pedro Magan. I'm a PhD student in computer science, and in this channel we talk about AI and machine learning in our everyday life and how we can use it to make our life easier. So in this video, I'm going to talk about the part 2 of the project that we already talked about, which is the event sequence and then predicting a sequence after that, which in this case is the score. So we have a sequence of data which are the log of different user or students interaction with a quiz, and then we want to know, without knowing what questions did they answer and what is the actual correct solution, try to come up and understand what is their score just based on their interaction trend. In the previous video, we saw that the R2 score is not very high, and then the error and maximum error are actually large with the vanilla version of the BERT. So here, the first thing that we want to do, we want to simplify the model. So how you can do is that when you don't have enough data, what you can do is that you either increase your number of data or you decrease your model capacity. Now, and if that's not somehow managed or trade-off between them, there would be some phenomena such as overfitting, and you won't get the best result possible. So for that specific reason, what we are trying to do is that try to reduce the model capacity. The original model of BERT, somebody already come with a distilled version of it, which they use as the student teacher architecture, which using a smaller size network and try to just learn and use some pseudo features in their feed-forward path, and somehow the student one, which is the distilled version, try to somehow mimic the behavior of this larger model. So we can come up with some model that is a lot smaller but have roughly the same performance. For that, we can spin up the VanDB. I'm not gonna use the VanDB for this part, so we're gonna ignore that part, but here we can use the distilled BERT tokenizer and also distilled BERT sequence to sequence classifier from the transformer of Hugging Face again, and I load the tokenizer from pre-trained of this BERT tokenizer, and also load the model from this distilled version as well. The next thing we need to do, same as before, I need to add this new tokens that I created before, which is basically the encoded version of the different actions that the user can take, and then since it was not already in the model, these are new tokens and it should be added to the previous vocabulary, and then we need to resize the embedding as well. So the embedding value that we already have for this new tokens list are actually completely randomly selected. So there is no pre-training there, but there is still pre-training in the higher level for the self-attention and cross-attention. We have some optional step in here. I'm not gonna run this one as well, but this one actually try to change the head node of the model. So every model in the Hugging Face transform architecture have some different components, and usually you can access them by calling the specific functionality. So in here the dot classifier actually return the head node, and I can replace it with a sequential model which has a dropout of 0.3 and then the linear layer. Originally it has the linear layer, but I believe that the dropout is slightly lower, so it's around 0.1 or something, but we'll try to increase it. So that's the way if you want to increase the dropout, but this is not necessarily gonna improve the performance. The dropout basically is one way to actually inject noises to the system, so increase the robustness of the model and kind of avoid the problem of overfitting. The warm-up, we already talked about it as well, is used because in the beginning we don't have a lot of useful information, and the weights are completely random, so the values that we get for gradients are not completely valid. So if we go a lot in the direction of those inverse of those gradients with the current learning rate, we might gonna just go in the wrong direction. So in the very beginning we are going to be a lot more cautious, and then after that, after the warm-up, we are trying to increase it. I have trained this model before, so I can show you guys that the Distilled BERT actually provide a slightly better performance in terms of our validation, which is basically something that we care about, even though their training loss is almost the same. So we see that in terms of validation loss, we have improved the result. Now we go back to the VS Code and try to create a qualitative result. Here we first create our heat map. Again, what we really want is to have the highest number of values on the diagonal and the least number in the off diagonal. We can see that we see a little bit of improvement in the number of misalignments. So the concept of curriculum learning comes from the fact that even us human will try to first learn something that is easy and then gradually go towards some more complex tasks. And so this is not necessary for this specific problem. This works for any learning task that you have. Don't try to start from something very big. Try with something smaller, gradually learn that, and then go to something harder. So what is the meaning of hard in our test cases? I would say that the hard would be some sequences that are larger, right? So if the sequence is larger, it is considered a harder problem, and if it is the sequence is shorter, for example, a few just interaction log in it, it is probably an easier one. So what we will do is that we need to create a new basically data set in here. So I call it curriculum data set. So in the init, same as before, we have the sequence score tokenizer and maximum length, but we also create something called complexity. So what the complexity in here is just the length of the sequence for the sequence in here. And then what we will do is that we sort, we call this internal basically function in here, which try to sort our sequence. So our combined, which is the combination of the sequence and the score and complexity, are actually right now sorted based on the key of complexity. So the smallest complexity will come first, and then a larger one will actually go later. So that's why when I zip it and try to look at the different components, right now they are actually sorted in the order of their complexity or their length. So the other method was same as before, the len and the get item, same as before. I created the use the encode plus to actually encode those to automatically add the special separating tokens, the maximum length and padding and so on. And I returned the dictionary of input ID, attention, mask and labels, which is required for the model. So now what I need to do is that I need to call this dataset instead of the previous one. For the reproducibility, I again need to call all of these different seeds and then we call the random split, and my train and validation right now are based on this train dataset that is generated from the dataset that was from the curriculum one. So right now, even though that it doesn't seem that much change, but we can see that our result actually will improve a lot. I didn't change again the learning rate or any warm-up step, everything same as before. I have trained this one as well, so if we take a look at it, the curriculum result actually improved the performance a lot. So compared to the two other approaches, the validation actually decreases a lot. So it shows that okay, this one is basically working. And if I look at the confusion matrix in here, I see that the less elements are actually off diagonal, but still there are a few. What we can do further than this? So any fine-tuning that we are doing right now will do and update all of the weights. So what's the problem with that is specifically in some downstream task, when you're using a foundational model and you're doing any downstream task, if you are doing on one task specifically for too long, something happen called catastrophic forgetting. So that's when you are too much training one task and it's kind of forgetting whatever general knowledge that it has from before. So that's why they said that when you are doing the fine-tuning, either try to do a combination of different tasks at the same time rather than just one task, same as right now what we are doing. Or what you can do better is that instead of updating the whole key Q and value in our attention, we try to convert them to a smaller multiplication. Right now I have two matrices, but each of them has a smaller number of weights. I can just work with this part of the matrix manipulation and then update only this part instead of updating the whole number of parameters. But everything in here will be done automatically for us with the PEFT. So PEFT is a library from LoRA that what they do is that you give them basically a model. It will compute its PEFT model or parameter efficient fine-tuning model, and then to mention that what are the parameters that you want to consider as your target module. For example, here I'm going to say any linear module. I'm going to consider them as a target module, and then do you want a dropout, and then the LoRA rank, or this one 8 is the one that I talk about, like what you want to reduce them to. 8 is something that usually people chooses, and then consider the bias to be what will happen here is that, let's say for our BERT model, which is around 110 million, or for Distilled BERT, which is around 68 million, now my trainable parameter is only 1.3 million. This is around 2% of the original number of parameters. So instead of training the whole number of parameters, which requires a lot of data, which requires a lot of resources, which is going to be very time consuming and can be prone to the catastrophic forgetting and so many other things, right now I just need to update around 1.3 million parameters, which is going to be a lot faster. And this LoRA can actually be considered as a specific module which I can add or subtract for different downstream tasks. So I kept the same model, and then I add or subtract this LoRA to make it adaptable for this specific downstream task. So that the other process are the same. We use the optimizer, the steps, and the scheduler, and we try to do the training. I have the result for LoRA training as well. So if you look, the result for LoRA is deteriorate the performance a little bit, and it's kind of expected because we are training around like only 2% of the parameters, but it is still worth it because it requires a lot less number of compute resource, and it is also more efficient. So if we do the training a little bit more, we can even improve the results. So here is basically the confusion matrix, and here is the value for the error bars, and basically the final value of R2 score and MSE. So what we really need to do, we cannot do much more in terms of the model. So what is our bottleneck right now? We kind of understand, okay, our bottleneck is the data, not the model. What needs to be done is something called data augmentation. So for data augmentation, the approaches that is done is similar to the pretext in contrastive learning. So in contrastive learning, you try to create a pair of similar and dissimilar terms and try to enlarge the ones that are dissimilar in the embedding layer, and then try to close the one that are similar, semantically similar, inside your basically embedding size. So giving different views of the same data will actually improve my ability of for example of context learning, or basically representation learning. So what we'll need to do in here is that I will try to come up with different views of this sequence, and try to let the model know that, okay, if this change a little bit, this is still okay. For example, let's say I have different time sequences. If I change the time, for example, the T1 change to T2, is that gonna change a lot my result at the end? Probably not. Or if we miss a little bit of for example, result from the beginning, or from the somewhere in the middle, if some of the actions are not taken, for example, specifically if it is interacting with a Streamlit or interacting with other toolboxes, is it gonna really affect the final result? Maybe, but maybe not as well. So to do, I need to create a new sequence, which is called augment sequence. This is before the data set. I created an augment sequence. And how it works is that I will try to look at the different sequences. If it is Q, we don't want to change the problem. If the problem changes, the whole score also changes. So we don't want to tweak the Q because that's kind of like sensitive. But if the token is T, then it is time interval, and I can actually kind of like randomly try to update it and put some new value for it. And the same goes for other tokens. And for other tokens, what I will do is, based on some probability, if the probability is lower than that, I'm going to extend it. Basically, in a simplified way, we are going to either change some randomly time interval, or I'm going to skip some action, or randomly basically insert some action. So changing the time can extend some action or shrink some action. So based on that, I can basically augment my data from 254 to around 778. So I created some pseudo data set based on this contrastive learning that is basically going to have a similar output. This different view of the dataset will help the model to better understand the context and how different components are working to each other, and we're also like increasing our dataset, which was basically the bottleneck of our approach. So I will call the curriculum dataset, which is new augment sequence. You can see it has improved the results and actually show that okay, this can be useful. And here we can also create our confusion matrix. So our confusion matrix would look like this, and then our error bars. And there you have it, guys. We went over different approaches that we can try to improve the result of the event sequence learning and try to predict the outcome based on the sequence. If you guys have any more suggestions that I can try, let me know in the comment and I will try it and let you know how it works. I have put the link of the code for the GitHub. Thank you for watching until the end of the video. If you enjoyed it, make sure to like the video and more importantly subscribe to the channel so you get more information about the projects that I work on and some information about AI and machine learning in general. If you want to watch the first part of the video and you haven't watched it already, make sure to watch this video that I created before, which I went over the different steps and thought process on how to solve a problem and how actually set up the environment and everything. So it's a good resource that you can watch. Let me know in the comment what project or work you want me to focus on next, and see you until the next one.